Good morning. Sorry for the delay. I noticed there was something I'd left out. So I was correcting it. But I can see we are only 30. We still have about 7 students or 9 students not logged in. Let me save the number of students we have as we start. For yesterday. I can delete this. The names. So I have a question note there, but I think we'll start. I'm hoping they will join us. So last time we were looking at the narcotic analgesics. We will continue on the same. Let me get the slide where we got to. Just not yet. There. I think you were able to get up to slide around 22. You were able to get up to. So we were looking fast. I decided let's first of all have an idea of the general, very general SARs before we look at each of the changes specifically, and of course also giving the necessary examples. So you are looking at the very, very general SARs of morphine and analogs, and we'll be looking at morphine and analogs and even derivatives. We mentioned, I hope you can remember, we also mentioned the morphine rule. And as we look at all the analogs and the derivatives, we will check to see also whether they obey the morphine rule. Occasionally, we do have exceptions. I don't want us to do a big recap so that I spare my voice for what we are going to do today. So I think we already looked at this slide number 20. So let us look at number 21. As I'm saying, we are looking first of all at the very general, the general changes that you can do to morphine to get its analogs. And the analogs either will have more activity or lesser activity. They even can have Remember, we did mention the more the analgesic activity, also the more the toxic activity. The lesser the analgesic activity, the lesser toxicity. And of course, some of the negative effects of morphine is what we said. It causes addiction, it causes tolerance, and it causes dependence. So once you have very high analgesic activity, you expect also those other negative effects to be on the higher side. So we are now looking at still the general SAR, and we are saying if you put a hydroxyl group at position 14, and that hydroxyl group at position number 14 usually carries a beta orientation. Remember, we numbered this compound. This is our 13, which we call the quaternary carbon. This is our position 14. If you put a beta hydroxyl group here, that means that hydroxyl group carries a wedge. It is not like it carries a wedge. It is not like this. It carries a wedge. Beta hydroxyl group. Then there is an increase in activity. And when you put a hydroxyl group at position number 14, the resultant compounds are called oxy. So we are saying the oxy compounds will have much, much higher activity than most of the other compounds without a hydroxyl group at position 14. Again, general, we are going to look at examples in a minute. Removal of hydroxyl group at position 6 also increases activity with the increase of activity, because when you remove that hydroxyl group, you increase the lipid solubility. It means that hydroxyl group is not necessary for activity. Remember, we said that hydroxyl group and the benzene ring is necessary. So the 3 hydroxyl group, the benzene ring, necessary for activity, the 6-hydroxyl group, not necessary for activity, you can remove it and you will still retain activity. Then oxidation of the hydroxyl group. So there is also this hydroxyl group. You can also oxidize it to a ketone. When you oxidize it to the ketone, you get the ones, the morphonones, the codones, and so on. Remember, one means a ketone. And at the same time, when you just oxidize it and leave this unsaturation at position 7-8, you find that the increase in activity is not as much. But that group there, in other words, you add two hydrogens, a hydrogen there and a hydrogen there, remove the unsaturation and also oxidize the hydroxyl group at position number 6, there is quite a lot of increase in activity. And therefore, the hydrocodone oxymorphone will have much higher activity than the dihydromorphine and so on. So the oxidation of the hydroxyl group to ketone group activity, there is also reduction of the 7-8 double bond, e.g. hydrocodone. Of course, remember, reduction is addition of oxygen and also addition of hydrogens. Addition of hydrogens or saturation is also a form of reduction. So if you reduce that 7-8 double bond and also do oxidation of that position, again, you increase activity. Note these compounds, we'll be calling them the own because of that. We are calling it the two hydrogens there. Acetylation, again, we are looking at general. Acetylation of the hydroxyl group at position 6, acetylation will increase activity. When you acetylate that group there, again, you are increasing lipid solubility. So this group is not very favorable because it reduces lipid solubility. Remember, it is a polar. It's a polar group because of the high electronegativity of the oxygen. It is a polar group, and it increases the water solubility of morphine, and it really is not necessary for binding the receptor. So once you remove it, once you mask it with either an acetyl group or even an ether group, there is increase in activity, but more so when you use an ester than an ether. Removal of the ether linkage produces compounds called morphinans that has increases activity. That now will be giving us the morphine derivatives that we are even saying you can remove this link here. Remember, this was our ring D. You can't remove this link here, the ether link, and you will get the morphinans. And the morphinans have been found to have more activity. You will get examples of examples such as the levofanol. They have much more activity again because this link was just found again. It is not needed for binding the receptor. It is not part of the pharmacophore. It increases lipid solubility. So removing it again increases the lipid solubility of the derivatives, giving the morphine derivatives much higher activity. As I have said first, oops, goodness, where have I gone? Oh, yes. So as I have said first, we're just looking at the general, and then we are now going to look at each of those structural modifications. So we have just mentioned, and you have an idea of what happens when you change this. When you modify these groups, but now I want us to look at each and every one of them. So this is our morphine. That is our structure of our morphine. And what are we saying? We are saying we can do modifications at several areas. The first modification we can do is on the alicyclic ring. We can do modification. This is the alicyclic unsaturated linkage. We can also do a modification at that position. There's also our alicyclic ring here. So alicyclic, the whole of this ring here is an alicyclic ring. It's a cyclohexene ring. So we can do modification on that ring at that double bond and also at position number 6. We can also do modification at position 14. I hope you're starting to get these points. At position 14, this again is also an alicyclic ring. It's not aromatic, it's a cyclohexene again ring. So we can also do changes on that position there of that ring with change in activity. So there are quite a number of positions we can change in the alicyclic ring. We will also see that we can also link. We can also link position, I think it's 14 and 6. We can and also still retain very high activity. So we are saying one of the changes we can do is modification of the alicyclic rings or alicyclic portion of morphine with either with increase in activity or decrease in activity, depending on which group you can do. You can also do modification on an aromatic ring. We have looked at this aromatic ring, and indeed the only change, of course, even this one is an alicyclic ring, and you have said you can even remove the interlinkage. So the only here is on the phenolic hydroxyl group. No other change is allowed. Most of the other changes will result in a decrease in activity, not unless if you are using what we had said earlier, an isoster. But preferably, the benzene ring is the best in terms of activity. So phenolic, aromatic ring, most of the major change is just the substitution on the hydroxyl ring, and we look at one on each one of them to see the different structures that you get. You can also do modification on the tertiary nitrogen. You can see here we have an R, but you can see we are saying it requires to be a tertiary nitrogen for maximum activity. Should you put a big group? Should you put a small group? Should you put an aliphatic group? Should you put an allele group? Should you put an aromatic group? What are the changes that you get? We will look at all those changes and decide and understand the influence of the structural modification of morphine on analgesic activity. Remember, we are looking at narcotic analgesics. So our aim is to do structural modification on morphine to have an influence on the quality of their activity we get. We talk about the quality, we want the molecule to have minimal dependence, minimal addiction, minimal tolerance, of course, and have maximum analgesic activity. Unfortunately, as we have already said, more often than not, you increase analgesic activity, you increase the addiction, dependence, and tolerance. So those are the different various areas you can change. You can change the tertiary nitrogen, you can change that alicyclic linkage, you can of course change position 14, you can change also in this ring, you can make it a bicyclic ring, you can change also, and you can change the 3 hydroxyl position, and for sure you can also remove the interlinkage. So I want us now to look at that one by one and also giving examples for the same. So we want first of all to look at peripheral modification, peripheral modified morphine, and we want to look at ring A analogs. Remember we said it is A, B, C, D, E. So E as a prepared the aromatic ring. Hope you can hear me. There's no problem. So we're looking at ring A. So we are saying ring A, which is the aromatic ring A, and its 3 hydroxyl group are important structural features for analgesic activity. So not only do you require ring A, which is aromatic, you also require a free 3 hydroxyl group. And even if it's not free, so when you're giving it, it is a esteric, and that group compound, like heroin has activity, remember that drug will act as a prodrug. When it gets into the body, it must be cleaned to give you a free hydroxyl group, which is indeed required for binding of the receptor. Removal of the 3 hydroxyl group reduces analgesic activity. So it has to be there. If you remove it, it will reduce activity. Esterification of the carbon 3 hydroxyl activity, like in codeine. So when you esterify an ether, when your esterification is putting an O, like OCH3 or C2H5. So when you do esterification, Then you reduce narcotic and analgesic activity, and the larger the ether group, the lower the analgesic activity. So that is important. We are saying etherification will reduce activity in proportion related directly proportional to the group of the ether that you have put. However, these compounds that you form, like codeine and its derivative, have antitussive or antitussive activity. And indeed, that is why they are used as cough suppressants. So you can see structural modification of morphine giving us a new or giving a new set of compounds which have differences or different pharmacological activity. Of course, the codeine also does have a little bit of addiction, but very minimal, because we said the lower the analgesic activity, the lower the lower the lower the analgesic activity, the lower the toxicity. But it does have a bit of it. It does cause addiction, does cause a bit of tolerance, and indeed codeine has really been used. It used to be, and again, do remember, and we have said severally, that the way you react to a drug depends on, and we said, I think yesterday when we were looking at the anti-cancer, so that sometimes it depends on your genetic makeup, on your sensitivity. So you could take codeine, and not one person can take codeine, no have issues. Another one takes codeine and they'll sleep the whole day. So again, remember that we do have differences in the way we respond to drugs because of our differences because of the genetic differences. And as we said yesterday, in the pharmacokinetics in our bodies because of what we call the polymorphism. So we have codeine, which I believe now in most drugs, in most countries, it has been withdrawn from cough syrups, as I have said, because of misuse. We used to make, in fact, at the time I was working in KNH, we used to make what we call liters codeine. And I'm telling you, it never used to last. You make a whole drum and 10, 15 liters, and within a very short time, there is nothing. And you haven't even given it to the patients. So we had also quite a number of our staff members who are addicted to these things, and quite a number of them also working in the pharmacy. Of course, some of them were not themselves addicted, but they were stealing. And that happens in many hospitals. And I hope, my dear students that have taught will not do that, but it will not be them. Because we also find that some of these drugs are not even, it's not that they're abused, but when they are made, the people who are trusted to give them to the patients actually sell them. And that is us, the very professional people. You find there's a black market. Very sad. A very sad affair indeed. So it is my prayer that when you go there, out there, your work will not be to deny the patient's drug, as I've always told you before. It is my prayer that your work from JCOT, we have had very nice, very wonderful praise of our students out there. It is my great prayer that your work will be to safeguard those drugs. Because you always remember, it doesn't matter how did you become. But what we have done, the legacy we have left, will be shared or will be passed on from one generation to another generation. The curses we leave, again, will be passed on from one generation to another generation. So work hard, yes, work very hard, but kindly don't be greedy. I'm not teaching you these things. The morphines, how they cause hallucinations, you fall here. So that you go out there and trade them. So that you go out there and take them for the benefit of the patient. So please be careful, because these things can make you a cabbage. Oh my God, this thing is coming back, and I was so good. Yeah. Oh my goodness, Jesus, just help me to be able to go on. So now we have, this is our morphine, and all we have said is that, where is it going? So that is our morphine. Has misbehaved. I don't know why this home is so harsh on me. But it's usually harsh because also of the talking. How do I add my brain without talking, surely? So this, we have said, this is our morphine, and you can see it has a 3-hydroxyl group, and we are saying if this morphine, its relative activity is 1, then you can see the deoxymorphine relative potency is 0.1. So we are only saying removal of the 3-hydroxyl group to give the 3-deoxy. Deoxy, DE, di means 2, DE means removal. Deoxymorphine has much, much lower activity. Again, this is our morphine, and we have only now we are on, see, I told you now when we go one on one, you look at each one of them, we will also give the examples so that you understand better. So again, here we have our morphine, and you can see this is esterification, where the 3-hydroxyl group has been esterified to methoxy, 3-methoxymorphine or codeine, simple codeine. And once you derivatized it in the codeine, you do not have to have your free hydroxyl group. You can see again relative potency decreases a lot to 0.15. So it sees it still has analgesic activity. That's why we have said it will also have minimal toxicity. Again, if you put an ethyl group, again, you can see relative potency decreases much more because we say the decrease in activity is directly proportional to the group. Of course, the ethyl group is much larger than the methyl group, and therefore much more decrease in the analgesic activity. This group here, it is a bit misplaced. This is a morpholine. So here, this oxygen, kindly note it's here, you can draw it properly. That oxygen is at that position there. And then you have the nitrogen, and then you push this CH2, should be up here soon, or you can push this down. I will try that to make it. So you have N, CH2, CH2, and then O, and then continuous to give you 4-codeine. So 4-codeine, this is a morpholine structure, and then here CH2, CH2, O, and join to the 3rd position. So this is the oxygen which has come from the hydroxyl group. So you get 4-codeine again. The larger the group, the lower. And now just
hello, Dr.
Yes. Yes.
We explaining. Could you kindly put it on?
What? The what?
The cursor.
Okay, just
the red dot.
Okay, just a minute. Okay, you don't have the cursor. Where did it go?
Yes.
How do I get it? Let me look for it. So let me do. Okay, thank you for notifying me. You know where I should get it from? You are the digital guys. Trying to go down. Just a minute. Let me see public. Where do I get it from? Meeting. Where did it go? You know where I can get it from? Anybody?
No, I do not. I have here.
Oh my goodness. Pluto users, white clothes. It should be somewhere. Options. It's not big full screen. And when I make full screen, Asa is not there. Interfere with it. See whether it comes. See whether I can call for help. Hello, students. Hello. Can you hear me? Can you hear me? Can you hear me?
Yes.
You can hear me. Can you see the pencil? Hello, students. Any of you who has a microphone on? Any of you?
Yes, we can hear. Yes, we can hear you.
Can you see the pencil?
No.
No, you can't see the pencil. Let me try again. Did it? Jerry? Hello, class. I hope you can hear me. I will use my pencil to mark. I hope you'll be able to see. So the group. So we go back to Focoday. So we are looking at this group. So I think it is a bit more work, but I'll use it to mark the Focoday because I can't get that group. That's circular indicator. So this is the Focoday. So what I was saying, this oxygen, in fact, it is even easier, should be there. To be your oxygen, and then this group, all of this group, is you move it to here. I hope you have understood. And then now you continue. Is it clear? So here the oxygen is at that point, and then nitrogen, CH2, CH2, oxygen, and then now you join them there. I hope now you have understood. Is it clear? Is it clear, class? Is it clear?
Yes.
Yes, so that's what we mean. So the whole of this group has been displaced. So you push it back, and oxygen at that position, as I've shown, this CH2, move it back, and then you join it there. And what we were saying is that the analgesic activity, which of course corresponds with the toxicity, is directly proportional to the size of the substituent at position number 3. And no wonder, if you look at our 4-codeine, you can see that its relative potency is 0.01, much lower than the relative potency of ethylmorphine, which is 0.1, lower than the relative toxicity of codeine, which is 0.15. So I hope that makes it clear. Thank you. Then we're looking now at codeine is available. So now, because I've introduced codeine, I thought it's important. Let us look at it. Because indeed, as we have already seen, it's a very important drug. It is even used in combination with quite a number of tablets as an analgesic. And therefore, it is indeed an important drug. So it's important for us to have an idea of what it is. And we are saying it is a sulfate. In other words, the codeine will be formulated as a sulfate of phosphate. And then remember, we formulate these drugs, especially that they are mainly hydrocarbon bases, not bases of basic, but they have a hydrocarbon base. They are highly lipophilic, so we derivatize them into the salts for increase of water solubility, because urines, of course, require them to have water solubility for purposes of them getting into solution. As a free base, it can also be given as a free base, which, of course, as we have said, will have issues of water solubility. It can be given as tablets. You have codeine tablets. It can be given as an elixir, which, of course, means it has a lot of alcohol. It can also be formulated as a solution for injection. So it can be formulated, different formulation, depending on the use. The 3-methoxy group protects the 3 position from glucuronidation. Remember, we did say morphine, the major route of metabolism, and we did mention about its fast-pass effect, even before it gets into the liver. Because of that hydroxyl group, it undergoes rapid fast-pass effect and therefore decreased activity. So we are saying the 3-methoxy group protects the 3 position from glucuronidation, as in morphine, giving it a slightly longer duration of activity. It is used as an analgesic and antitussive, and of course analgesic and antitussive, because we are saying it is better. It has slightly lesser toxicity compared to morphine, and of course, because of the change in structure, it developed the antacids activity. It is metabolized by cytochrome-mediated oxidative O demethylation to morphine. So slowly, it will be metabolized to undergo oxidative O demethylation to give you the morphine. And no wonder it will increase. There will be increased toxicity because one of the metabolites, even low concentrations, is indeed morphine. It will also be metabolized by cytochrome-mediated oxidative N dealkylation to norcodeine, removal of the N-methyl group up there to norcodeine, of course, with the decreased activity, of course, also conjugation to the 6-O-glucuronide. So very similar to the metabolism that we had seen with morphine. It is, of course, only that, of course, now the one position is blocked. So, of course, it cannot undergo oxidative O methylation at position number 3. It cannot only undergo oxidative O demethylation because the methyl group already is there. You can derivatize that position 3 also using. You're saying you can't see the pencil at all. Can you see the pencil? Hello? Hello, class? Hello, class? Can you hear me?
The pencil is visible, but the small indicator is not visible.
But you can see the pencil?
Yes.
Fine, because so then it's okay. See, I can move the pencil.
Yeah.
Yeah, so that I can move. It's the same. The function is the same. That's what I was asking you, whether you can see the pencil. So we are on point number 1, that's the revitalization of the carbon 3 hydroxyl group. Again, this time not esterification, esterification. So that's one very important, esterification. By esterification, I don't want to, increases analgesic activity minimally. And of course, why esterification is increasing analgesic activity minimally is because when you do esterification, you increase the lipid solubility of that molecule a little bit more than esterification. So what happens is that the resultant molecule will penetrate the lipid membranes very rapidly, get into the body, get into high concentrations, and of course, therefore giving you much higher activity than expected. Of course, then reaching the high quantities, of course, it is going to be derivatized, it's going to be metabolized to give you the morphine. Esterification or acetylation of both the 3 and 6 hydroxyl groups yields heroin. I believe all of us have had that drug. Heroin, very potent analgesic drug, and very highly abused. This again is because you have esterified the 3 hydroxyl group, you have esterified the 6 hydroxyl group. It is not the molecule that is really having the high activity. What is bringing about the very high activity is the very high lipid solubility of heroin. The very high lipid solubility of heroin allows it to penetrate the lipid membranes very quickly, to be distributed into the brain very quickly, to reach very high concentrations in the brain, and then it will undergo degradation, it will undergo metabolism to give you morphine, which will give you the very high activity. So please do understand, just as the next point states, that the primary factor involved in increased analgesic potency is the increased lipophilicity and distribution to the CNS. So this drug is rapidly distributed to the CNS, high lipid solubility, high concentration. Definitely it's going to be metabolized to give you morphine, high concentration in the brain, and therefore giving you very good activity. Heroin is metabolized primarily by hydrolysis of the carbon 3 O acetyl moiety to 6 monoacetyl moiety, 6 monoacetyl moiety. Like now this one, how did it come there? I don't know why it's not accepted, but I'll look for it after this. So 6 monoacetyl morphine. And of course, when you have the 6 monoacetyl morphine, as long as the 3 acetyl groups, so the first one is the 6 so the hydrolysis of the 6,3 O acetyl group. So the minute the 3 acetyl group is metabolized, the molecule, we said, it only requires the hydroxyl group at position number 3. So definitely it will already acquire very good activity. And then of course it can also be metabolized to the 6 monoacetyl morphine. The 6 monoacetyl morphine may be further hydrolyzed to morphine, which is conjugated. Of course, now once you get to the morphine, the story is the same. The metabolism as we discussed before. So the only different metabolic process of heroin is the hydrolysis of the acetyl groups, the 3 acetyl group and the 6 acetyl group, to give you the monoacetyl morphine, either the 3 or the 6, which depending on which has been hydrolyzed, and of course then the morphine will be further metabolized to the other ones that we had said, glucuronic conjugation, oxidative and dealkylation, as we had earlier discussed. So that is the metabolism of, or that is the SAR of the 3 position and the 6 position, and I have given you examples of the groups that you can get. Indeed, even the metabolism is here. You have that is our morphine here again, and you can get the 6-deoxymorphine. So 6, or you can, this is structural modification, morphine, you can change it to 6-deoxymorphine, and you can see we are saying the relative potency, as we had already said, much higher because of increased lipid solubility. You can derivatize into 6-methoxy-morphine. Again, as long as that group is free, that you have masked the water solubility, slightly increase the lipid solubility, and therefore that compound is expected to have much higher analgesic activity. And then you have again this group. Of course, now this group is much bigger, and of course, once you put very big group, do remember that compound is subject to steric hydrants, not being able to approach, not being able to access, not only approach but access the receptor effectively, and that is why you'd expect that we have a slightly decrease in activities because of the steric hydrants, a bulk group, steric hydrants, the molecule not being able to access the receptor very well. And then you can see here, you have the hydroxyl group and you have the acetyl group. And indeed, we did mention that when you put the acetyl group, also there will be much increase in activity because of the fact that, again, there is increase in lipid solubility, there is masking of that group. And when you put both of them, of course, we did mention that even then you get heroin. And heroin, as we see here now, again, morphine, 3-acetyl-morphine there, acetylmorphine, we say it's slightly, you are still saying 1.0, slight increase in relative potency compared to morphine, very slight, because do you remember we are saying, yes, it will increase the lipid solubility, but because of the time you require to hydrolyze it, then it has only slight increased activity. But the minute you acetylate that, and you acetylate that to get the diacetyl, you find the compound is has double the analgesic activity of morphine because of the increase in lipid solubility, as we have already discussed, and increase in distribution to the CNS. We are still on the alicyclic. We are not yet through the peripheral alicyclic groups. So we have done that. So we are still on ring C. We are not done with ring C. We are still on ring C, the peripheral groups. And the next one is the alicyclic double bond. And we had already mentioned that you have the 7A double bond of morphine is not required for analgesic activity. If you oxidize the 6-hydroxyl group, so oxidation of the dihydromorphine is morphine without the double bond, and you oxidize its 6-hydroxyl group to give you the morphone. So these are two activities at the same time. You have saturated the double bond, 7A double bond, and you have oxidized the hydroxyl group at position 6 to a ketone. That gives you hydromorphone. The hydro here, the hydro is because of the addition of the two hydrogens, and the morphone, the on here, is because it's a ketone. Then you have further increase in activity. So in other words, the single activity of saturating the morphine does not really increase activity. The double activity, saturation plus oxidation. Of course, the oxidation, what it does, it lowers the lipid solubility. The ketone has lower lipids, it lowers the water solubility. Sorry, the ketone has higher lipid solubility, lower water solubility than the hydroxy group. So it increases the lipid solubility, and of course also there is saturation. The substitution of a 14-hydroxyl group, and when you substitute again the 14-hydroxyl group, the resultant compounds are the ones we call the oxy groups compounds on the hydromorphone structure, as in oxomorphone. So the resultant compound will be the oxomorphone. So oxymorphone is still the morphone there. So now you remove the hydro and you have the oxy because of the 14-hydroxyl group. But you can note that this compound will be saturated. So that's why we are not really bothered about the hydro. Position 14 for that compound must be saturated. Position 6 of that compound must be oxidized. And then you put a beta hydroxyl group at position 14. Beta hydroxyl group at position 14 gives you the oxymorphone. If you are starting with codeine, you get an oxycodone. So same thing, produces a further increase in analgesic activity, oxidation in the 6-hydroxyl group of morphine directly as in morphone without reduction of the 7 and 8 double bond does not significantly alter analgesic activity. So we have already said that you require us to go to the hydromorphone, oxidation, saturation, or reduction of the 7-8 double bond increases activity when we get the hydro derivatives, and then oxidation of the 6-hydroxyl group to the oxy again further increases activity. So kindly remember that those two positions are going hand in hand. Therefore, again, you have our morphine there, and you can change it to the dihydromorphine. To change it to the dihydromorphine is just to saturate the 7-8 double bond. You get the dihydromorphine. There's nothing else you have done. So the dihydro represent that saturation. Then you can change it to the hydromorphone. Change it to the hydromorphone is you have saturated there and there is oxidation. So it's a hydromorphone. Again, much more increased activity. But if now that hydromorphone, you put a beta hydroxyl group, this group here, it's supposed to be beta hydroxyl group, and this position here, beta hydroxyl group, and that position there, retaining the same structure as previously in hydromorphone, you get the oxymorphone, and you can see its relative potency is 10, much higher, almost double that of the hydromorphone by virtue of addition of that hydroxyl group at that position. Then, of course, you can convert this directly to the morphone. You convert it to the morphone is where you still retain that, and all you do is put that double bond. And you can see, indeed, the morphone has even much lower activity than morphine. Coincidentally, has much lower activity than morphine. You do require to saturate that group to increase the activity of those resultant molecules. Some of this are observed, sometimes not very readily explained, but these are some of the observations that are made when the drug discovery and development is being done. Of course, remember that is a methyl group. Then, since we have introduced some of these drugs, again, let's look at their metabolism. Their metabolism will be quite similar to what we have looked at. Of course, sometimes there will be some difference. You look at this hydromorphone, and this hydromorphone has a ketone there, and therefore this ketone can undergo oxidative, or can undergo reduction. That ketone can undergo reduction, and when it undergoes reduction, the resultant compounds which will be hydroxyl derivatives, can either carry the alpha orientation or the beta orientation. So you can have the dihydromorphine, you can either have the dihydromorphine, again it's dihydromorphine because you can see the hydromorphone does not, remember hydromorphone will not have that double bond because of the hydro. So it will either have the dihydromorphine, which can either have the alpha, this one here, class. This is our alpha orientation. Sorry. This alpha orientation here. This one there. Alpha orientation. Or you can have this, I'll just point at it that way. Or you can have that which has the beta orientation. So you can have this carrying the alpha orientation, or you can have that carrying the beta orientation. And both of them, so both of them will be metabolites. Or you can have the hydromorphone glucuronide. You can see this one is free hydroxyl group, so you can have the 3 glucuronide conjugation, and you can have the hydromorphone glucuronide. Remember, whenever you have a free group, by the time this one is undergoing its metabolism, this is already free. This group is already available for metabolism, and that is why it will undergo metabolism very quickly. And therefore, the glucuronide, there will be other products, but we're looking at the major products. There will be other products because when this, of course, it can also undergo this oxidative and dealkylation. But we're looking at the major products, but even the others can, of course, be present. Sometimes it keeps changing itself. Yeah. So those are some of the metabolites of the hydromorphone. But you see, there's nothing to cram. Looking at the structure, I believe you can be able to derive the metabolic products because the structures are not very complicated, I hope. Then we can say something. I don't know whether we did mention, I don't know whether we mentioned the SAR of codeine, so that I don't repeat. So we have it. So let's say measure the SAR of codeine. Is codeine. SAR of codeine. Of course, this again is something we have mentioned. I think we had even discussed this. The reduction of codeine 7-8 double bond as in dihydrocodeine. Of course, when you reduce the 7-8 double bond, you get just like the reduction, the SAR will be similar for that of morphine. So of course, the morphine, it's only that the resultant compounds will be derivatives of codeine. So 7-8 bond to give you dihydrocodeine increases activity, oxidation of the 6-hydroxyl group of dihydrocodeine to give us the hydrocodone, results in further increase in activity. The 14-hydroxy substitution produces a further increase in analgesic activity. This will give us the oxycodone. So we are saying there is similarity in the SAR of codeine with morphine. It's of course that the drugs that will be formed with codeine will have much, much, much lower potency as compared to morphine. But the SAR for codeine and the SAR for morphine are very similar. So again, you can have that's a dihydrocodeine where you have removed that group, and of course that it will have the hydrocodeine, because you have only done one thing. You are seeing the activity is not much, no, it's not increased. If you have hydrocodone, codeine relative potency is equals to 5. Hydrocodeine relative potency is 0.7. Then oxycodone relative potency is 1. Codeine relative potency is 7. What does this mean? Because I would expect the dihydrocodone to have much more activity compared to codeine. I would expect hydrocodone to have also much more potency compared to codeine, and I've also expect oxycodone. I'll confirm, because they're having increased activity. I would expect oxycodone also to have much more activity compared to also the codeine. So definitely these compounds, they will have much, much more activity, as we have said, compared to the original codeine because of the structural modification. And we have seen those structural modifications are very, very similar to that of the codeine. So I believe this is, when you compare this one, it has its relative potency compared to codeine is 1.15, relative potency compared to codeine is 5, relative potency compared to codeine again is 7. So you can see these compounds have much, much, much more activity. And that's what we expect, because we have said the SAR is very similar to the SAR of the morphine. The formulation and metabolism of oxycodone. Again, remember oxycodone, saturation at position number 7-8, beta hydroxyl group at position 14, oxidation at position number 6. That gives us the oxycodone. Again, it is available as a hydrochloride salt. And again, remember, the reason why we do these salts again is to increase water solubility for purposes of dissolution. It can be either in tablets or in capsules. It can be used also as an analgesic and an antitussive, and of course it will have much higher activity compared to codeine. And the primary metabolite formed from oxycodone is 3 conjugates glucuronide. So primary metabolite formed from oxycodone is its 3 conjugates. So for you to form the 3 conjugates, it means first and foremost, it must undergo reduction at position number. It must undergo oxidative N demethylation at position number 3 for you to get 3 conjugates, glucuronic conjugates at position 3. Remember, at position number 3, oxycodone, you have a methyl group. So you must first of all undergo oxidative N demethylation, remove the methyl group, and then after that, conjugate that position, and that is a primary metabolite. So when you see the 3 conjugates, of course, first of all, oxidative N demethylation must occur to give you, because to give you the free hydroxyl group which is required for activity, and then the conjugation of that 3-hydroxyl group. Hydrocodone, it can be, we are looking at the formulations. It is available as a bitartrate salt in tablets, again, all in such as syrups. You can look for the structure of bitartrate. So this is an organic salt in tablets and syrup. It has an analgesic again and antitussive activity. So most of the derivatives of codeine are mainly used for the antitussive activity. But again, due to their liability to abuse or high susceptibility to abuse, the only one I've really seen is codeine, because these ones we definitely have much higher likelihood of abuse. Metabolism, it can undergo oxidative O dealkylation, that is oxidative O dealkylation, oxidative O demethylation to hydromorphone. So this is removal of the methyl group, because remember it's codone, it's hydrocodone, it has saturation at position 7-8, it has a methyl group at position number 3. That is why it is a codone. So it can undergo oxidative O demethylation at position number 3, and the resultant molecule, which is hydromorphone, is also active. Definitely, we know hydromorphone will have even more activity than hydrocodone. Hydromorphone will have much more activity than hydromorphone. It can also undergo oxidative N dealkylation, that is removal of the methyl group at position number 17. Of course, that will give us no codeine. That means no methyl group and no codeine. The minute we said we remove the methyl group, the hydroxyl group at position number 3, decrease in analgesic activity. Reduction of the 6-keto group, it can also undergo, because it's a codone. You see, it's a codone. So just like the morphone, it can undergo reduction of the 6-keto group to either the 6-beta or the 6-alpha. As we had said, you can get the 2 epimers. You can get the 2 epimers or the 2, you can get the 2 epimers, either the 6-beta or the 6-alpha. And normally we call them either the 6-beta hydrocodone or the 6-alpha hydrocodone. So either they will exist, both of them will exist. The epimelic 6 alcohols can undergo oxidative O dealkylation. They can undergo oxidative O dealkylation to the epimelic hydromorphose. Again, remember, they are codones. Because they are codones, they have a methyl group at position number 3. They can undergo oxidative O dealkylation, more specific, oxidative O demethylation. So more specific, oxidative O demethylation. And if that happens, both of them, each of them, will result in either, if it's a beta, it will give you the beta. If it's the alpha, it will give you the alpha. So it will give you the hydromorphose, the alpha, or the beta. And all we are saying is that the methyl group at position number 3 has been removed through oxidative O demethylation, removed to give us the hydromorphone, and it's a hydromorphone because it still has a ketone. It's hydromorpho because the hydroxyl group, the ketone, has been reduced to a hydroxyl group. And one of the hydroxyl group, it could be carry alpha or beta orientation. Each of the 4 6 hydroxyl metabolites, because have each of the 4 6-hydroxymetabolites have pharmacological activity equal to or greater than the parent compound. So we have 4 of them because we have these 2 epimers. We have the hydroxyl group. We have the hydroxyl group at position number 6, and it can be the alpha or the beta. So each of the 4 6-hydroxyl metabolites, and we can also have the hydrocodons, again hydroxyl group at position 6, either alpha or beta, and we are saying that each of the 4 6-hydroxyl metabolites have pharmacological activity equal or greater than the parent compound, with the exception of the 6-alpha hydrocodone, 6-alpha hydrocodone, which has been found somehow to have much lower, which is 1/6 as potent as the parent compound. So it has been found that the 6-alpha codon, remember, it is a hydrocodone because it has a hydroxyl group. It has a hydroxyl group at position number 6. It has saturation at position number 7, 8. But we are saying most of them have been found to be either equal or slightly have higher activity than the parent compound. But coincidentally, the 6-alpha, so the alpha hydrocodone, one which has a methoxy group at position number 3, and an alpha hydroxyl group at position number 6, somehow has much lower activity than the parent compound. And of course, the parent compound is codeine.